Hey, Victoria, good to see you here. What chapter 5 problems do you want to do? We could definitely do some chapter 5. I was just sending the email out to the class. My face looks so shiny. Oh my gosh. Like it's hot in Texas. What questions should we do? Put on a little chill music right here as we get started. It's like so much shine. It's a bright day. We'll get Mubot up and working right here. What problems shall we do? I think there's some new ones here. So let's see. Let's get my Pearson up and going. My Pearson, chapter 5. What does the audience say? Whatever people want to do, you pick the problem. We shall do it. Chapter 5. We'll check it out. Let's see. I'm 2 minutes away from permanent, so I'll copy paste it when I get there. Awesome, awesome. Yeah. Let me get chapter 5 up. But if anyone's here, we're just taking questions right now. Come on, taking questions button. There we go. Taking questions. Ask away. Signing in, so I'm getting everything up and going. Looks to be good to go. Getting all the questions asked. Signing in. How was your week? It was pretty good. Got to relax. We had a good time. What did we do? Made some pizza. Watched a bunch of The Resident. The Resident is a good show. So watched The Resident. Made some pizza. I played some Elden Ring. So I got to relax. It was a really good weekend. Like, definitely, you know, any weekend you get to play video games and relax. That's a good weekend. I played Pokemon. Community Day was yesterday. I caught like Roggen Rolls. What are they called? Caught like 8 of those. So I had like a really good day and hatched a bunch of eggs. Now I feel like I'm all, it might be, this because I was outside just standing. I got a bunch of sun. So I'm so pale that the sun just burns me. But it was really good. How was your weekend, Victoria? It was a very good weekend. It was nice and relaxing. Did some work over the weekend too, but overall, I'd say good weekend. Like you gotta do a little work, a little work, sprinkle in a little work here and there. So, but got to relax. That's the most important thing. We're almost caught up on The Resident now. Then we got to finish Black Sails. We got new Rick and Morty, so we're behind on Rick and Morty now. Usually we're watching Rick and Morty like, oh, we should watch that tonight then. I don't know, with dinner. So it's not bad. It's like the new thing, you know, is like used to be you go to the dinner table and, you know, like eat dinner with the family now. Stressful upon I went to the game. Oh my gosh, what happened? UTK Vols football. Let's see. Woo! We won 34-27. Vols are 3-0, and next week is Florida. See, I'm so bad. I'm such a bad Tennessee fan. It's wait. Did the game says that's Pittsburgh. Wait, was that last week? What game was there? Did we have a game? Ball State. I'm so confused. We beat Akron. Okay. And at Neyland Stadium. Okay, we beat them 63-6. We decimated them. Wow. No, I'm so bad. I'm like a horrible sports fan. Like I don't know. I try to catch up and like see what's going on. I see what next week's Florida at Neyland. Oh. I think are we rated higher than Florida? I don't know why the thing I was looking at had the game wrong. It says, oh, it has in, there it is. I see it now. It's such out of order. This thing I'm looking at just has the games out of order. So Akron was our latest game. We destroyed them. And then Florida's next. And Florida's rated 20. And we're rated 11. LSU's not rated anymore? Huh. Interesting. I thought LSU was a good team. Thought LSU, I guess they're not anymore. But we're having such a good season. Watch my fantasy team. My fantasy team's projected to lose by 10 points, but I'm up 15 points. Who does my cousin have playing left? My cousin has her QB, Josh Allen. So that's bad. And she has Bills defense. So, sorry, Bills. I want you to get destroyed. What did Brady do? I didn't even see. Brady got 11, not bad. Colts got wrecked. Or, yeah, they lost 0-24. I should have picked whoever the Colts were playing. Were they playing Jacksonville? My defense losing points, but Jalen Waddle got 29 points. Really my only real standout. But A.J. Brown, my number one wide receiver. Need him to get some big points. Ryan Scoop. Soup. Hey, Stan Com, what's up? Good to see you here. Tony Pollard got good stuff, didn't play him. My QB is, I mean, Brady, did he win again? He won. Did he win the first week? I didn't even see. I think Patriots, not Patriots. What am I saying? Man, his completions are a lot lower this year. Brady's, he's like 50% completions. I remember one season he went like 30 passes in a row with completions. So that's, he's still Brady, still playing in the league at like, what is he, like 65, something like that. But good to see everyone here. Let's throw out 1,000 points. What should we do? I think we're gonna do some chapter 5 here in a moment. We should pull some up. We're just talking some sports to start out, and hopefully, sorry Josh Allen, but I don't want you to have a good game tonight. Josh Allen, I want you to be like, man, we thought the Bills were gonna have a good season. I want my cousin to be sad. Sorry, Mark. I want Mark to be like, what? The Bills started out so good. They looked so good last week, and now this week they're horrible. What? Bills season over. If you're working on something, staying calm, let us know. Whatever you're working on, tell us and we'll get started on it. Sorry, Mark. I want you to, next week, the Bills can be amazing. And I want you to be like, oh man, I don't know what happened. That 1 week was a hiccup. 1 week we looked so bad. Now we're so great. Let's say. There was a average score on stats midterm. Was points on standard and z-score. How many points did they score? It was 7 points from the standard deviation, -2 z-score. Okay. Let's go. Yep. I got one similar to that. Let's go check it out. Z-scores. So here we are. Where's our timestamp? Thank you so much, Victoria. Slouching. Let's go right here and go 10. 3. Stat 201, Chapter 5, Part 1 quiz. Or I'm doing the homework or something. Stats, scores, z-scores. Okay, let's check this out. Here we go. Okay, so what does a z-score tell us? What does a z-score tell us? Can anyone in the chat tell me what a z-score tells us? So if I see right here, we know that the stats midterm had this chapter is more convenient. No, and that's the thing is once you get it down, you're like, okay, it makes sense. You're like, okay. That's why I sent the announcement already about like chapter 5 today. It's not an easy chapter. It's not an easy one. The earlier ones are like, it's easy. Bar charts, pie charts, histogram, mosaic plot. Just got some terminology. You have to know how to read the graphics. So it says 77 was the average and 6 was the standard deviation. What does a z-score tell us? Well, let's look at the z-score formula to understand what a z-score is telling us. The way to find a z-score is the following. A z-score is equal to the observation minus the mean over the standard deviation. So just tell me, this is a what right here. If you subtract two values, you're just finding their what. Y means the observation. We'll plug some numbers here in a moment. Y means the observation. So, but subtracting two values just gets you the what between those two values. There starts with a D. I'm looking for a word that starts with a D. Subtracting two values will just tell you the what between two values. Subtracting two values will just tell you those values what. Difference. Staying calm. Great job right there. And so that's the difference. That's how far away are those two numbers. And then dividing by the standard deviation just standardizes it. So a z-score is a standardized difference. It tells us how many watts something is away from the mean, because this is distance from mean. Like that's just how far something is away from the mean, distance from mean. And then the bottom part right here is standardized units, so standard deviations. Like, so if you look at the formula, a z-score is always going to tell you what? So you have your distance from the mean, standard deviations. Just look at the formula and think about, oh, a z-score just tells you. So if you solve for the z-score here, what does it tell you? And then we'll look at our problem here and we'll solve our problem. What does it tell you? What is this z-score going to tell us right here? The z-score is going to tell us how many watts something is away from the what. So how many watts something is away from the what? Or the what something is in terms of watts. How many standard deviations something is above or below the mean? How many standard deviations something is away from the mean, right? So let's take a look at that with our problem right here and see how that applies, because in our problem, we get information. And the information we're going to help to solve right here is, it says the average was a 77. So if the average was a 77, this is mu. Mu is the average. Great job staying calm also. This is the standard. Oh my gosh. That's the standard deviation. This is the z-score. So you can solve this by backworking it. You can go -2 equals 2. We'll put here right here y, which is what we're solving for. We're solving for what was your score. And then the person got a 77. And then we have right here 6 is the standard deviations. But think about this. They're two. How would you explain to me their z-score? Like, just talk to me about what their z-score is. This person is blank blanks to the blank. Like, just when you hear -2, you'd be like, oh, their score is what? Knowing their score is a -2 z-score. Like, if you know they got a -2 z-score, they're 2 standard deviations below the mean. So we could draw it out right here. Draw your normal curve. Put 77 at the center. Go 1, 2, 3 standard deviations. We usually do 3. There's more than 3 standard deviations on the curve, but this covers 99.7% of the curve. Great job, Victoria and Kevin. Yeah, of course, Kevin. Ask a 3. Of course. Yeah. And as long as Brian can do his math correctly, the answer is going to be 65. That's where the z-score is at. So this would solve out to 65 right here. And that's my preferred way to solve it, like doing the drawing right here to figure it out. There are 2 standard deviations below the mean. So you can also alternatively solve the formula that in observation, this is a reworking of the z-score formula. An observation is equal to the mean plus the z-score times the standard deviation. That's a reformulation of the formula up top. Is it going to appear? What in the world? That was weird. This formula right here can be reformulated to write like this. But that's just what we know, that an observation, if you take the mean, add or subtract the z-score, because you start here at the mean and you would add the z-score and times it by the standard deviation, that's going to get you this answer right here. And so the mean, once again, is 77 plus the z-score of -2 times 6, that's 12. When you multiply those out, so that's 77 minus 12. And that's basically what you were doing up there by solving for 65 by literally drawing it out on the curve. So I think if you understand it in theory, it's better than trying to solve the equations. Just my name a few times. And so 65. Does that make more sense right there, Victoria? Really good trying to understand in theory what a z-score is and how to solve like an observation from a z-score, a z-score from an observation with the mean and standard deviation. But really good right here. If you know what a z-score is, then you can look at that and be like, oh, they're 2 standard deviations below the mean. So I just go -6 to the mean, and I'm at the observation. Yeah, Victoria, that's what we want. So we want to make, when you hear what a z-score is, you're like, oh, that's just somebody's amount of standard deviations above or below the mean. So what is the standard deviation? What is the mean? And then let me go up that many or down that many. Because a more complicated version of this question would say something like, see if you can solve this. Somebody, Corbin, good to see you here. Drop a question in the chat if you got it. A complicated version would say somebody's z-score is 1.666. So can you tell me, and then we'll do some MBA one next. Can you tell me what this person scored on the test? Somebody's z-score is 1.666, and then we'll do the economics one here next. Let me copy it. But see if you can find that while I get the... I'm going to grab this question right here. What would their score be? See if you can solve that. And I chose 1.666 for a reason. So see if you can solve that. Question 3. Let's do question 3 here in a moment. You got it. See if you can... What is somebody... If someone has z-score of 1.666, what would their score be on this test? What would their score be? Who can get that one right here? And then we're going to go on the next question. Chapter 5, part 1, homework. If someone has z-score of 1.666, so what does that mean? They are 1.666 standard deviations above the mean, right? So how would you find out how far they're above? So somebody here had a z-score of 1.666. There's a good follow-up to this. So someone has z-score of 1.666. So that's when you're going to have to, you might not be able to solve in your head, but we're pretending it said 1.666 right here. So what would be their observation? How would you solve this? Great job, Victoria. See, you get a nice job. So what I was probably going for 87. Multiply by the standard deviation and add to exactly. So if you notice, if you do the repeating, you'll get 87. Great job. That's what I want. I'm just doing more practice. Basically, if you can change this is when you know how to do the work. If you can change it and be like, well, I would just do the same procedure. So it's just practice. You have to make sure to be like, okay, I could solve it for another thing. Whenever you get time, 2C on assignment confused out of loop. Yeah, cool. Awesome. Let me take it right here. 474 2C. Okay. Let me write that down. Then we're going to do the next question. BAS 474. Assignment 3, question 2C, loop. Cool. We'll talk some about that. Okay, we got 2 more 201 questions. What's the next one? Corbin's, or someone else said one. No, wait. There's one more I thought. Where am I losing it to? Wait, Victoria asked one, and I thought there was another one. The incoming NBA. Question 3, there it is. Corbin asked it right there. Question 3, chapter 5. Okay, so is it this one right here? We'll do that one next. Okay, after this one. And then we'll hop over to Low 474. Incoming NBA. This one. Here we go. Awesome. So we got it. Okay, so the incoming NBA, and let me re-timestamp this. 20. Okay, so an incoming NBA student took placement exams. So we need to figure out the z-score for both of these. And it can get confusing because you're working with a lot of numbers right here. But a z-score is just going to tell us how many standard deviations someone is above or below the mean. Now, if the average of your class, or let me ask you this. If you took a honors chemistry test, great job, Kevin. If you took an honors chemistry test and made an 80, how would you feel? Let's say it's advanced honors chemistry here at UT, and you made an 80. How would you feel? And it's like the big final for the class. It's advanced honors chemistry. How would you feel? Advanced honors chemistry, and you made an 80. You've been doing all the work all semester, so you've been doing pretty good, right? Now let's say you take intro to basket weaving, and you make an 80. How do you feel on that final exam? Or it's just about baskets. It's just facts about baskets. Or that's the class. It's facts about baskets with Brian. Now you don't feel so good, right? But in both instances, I said an 80, right? Or if you take like a class that you're like, oh, I'm really good at, English, and you take an English class and you make an 80, you're like, oh, man. I mean, you're not like super mad at yourself, but an 80 doesn't mean the same thing. It needs context, right? So the way we give it context, and sadly we do this a lot of time in the world, is we compare ourselves to the average. So when you look over here, we got 2 different exams, and we'll highlight them with different colors right here. We've got here the economics exam. Now, she scored an 81, and then on the math, she scored an 89. So the mean of math, so let's highlight the mean of math was a 66 with a standard deviation of 13. And the color coding is really going to help us right here because the really confusing thing about this problem is you're working with 2 different distributions right here. So we've got economics. And what do you immediately notice about her scores right here? Where we have her math score, we'll put a Y right there. The mean of math, that is the mu for math, and the sigma is the standard deviation, which is the variation. So we have the average score, and then we have the variation. What do you notice about both of her scores right here? We'll do a little orange right here, and this is her mean for that distribution. And then we have, I'm assuming that is her score for that distribution. This is the mean for that distribution, and this is the standard deviation. She's above the mean for both of them. Great job, Corbin. That's the first thing I notice is that they, I don't know, he, she, they are above the mean for both of them. So good job to them, doing above average. Now the question is, if you look at this, whoa, don't do that. The question becomes, which of them did they really do better on? So if we look at this, we could take the mean for math, and I'm assuming the observation, minus the mean over the standard deviation. So we would put in the numbers right here for math, and we get that she made an 89. Notice how I'm taking the observation of the green. So I've color-coded everything to help me out right here. And then I subtract from it the mean, and then I divide by the standard deviation to give it context. So that's going to be about 1 point something, 1.6 or 1.7. We'll solve that here in a moment. Why not now? I say 1.68. So 89 minus 66 divided by 13, 1.77. 2 decimals. Let's hope it's 2 decimals. 1.77. So that's the math one right there. And then the verbal one, or the economics one, thinking I was doing an ACT problem, or SAT, 81. She scored an 81. And then we take the mean of her distribution, 72. And actually, no, it's still sevenths. Sevenths are interesting. So that's 3 sevenths. That's 42. So 1.42, I think. Wait, 28. It's close to that. Okay. Let's solve it out. 81 minus 72. Oh, it's 1.28. There we go. 1.29 rounded up. I cannot do math today in my head. So 1.29. Whichever has a bigger number above the mean than she. Exactly, because these both standardize it. Does that make sense? That's what we're doing here is we're standardizing this to say she was 1.29 standard deviations above the mean in economics. She was 1.77 standard deviations above the mean in math. So she did do better in math, like score-wise, and she did better compared to the mean and the variation, because this one has more variation in it. If she had made an 81 in this class, she probably wouldn't have, they should have done that for this problem. They should have had, she made an 81 in both classes. And then if she made an 81 in this class, it would have been, so that's theoretical if she made an 81. If she made an 81, then, and let me draw that right here. If she had made an 81 in both classes, because that would have been a more interesting problem, my Pearson. Come on, my Pearson. But does this make sense now if I do this? If she had made an 81 in both classes, which the problem doesn't say, she would have done better in economics. And this is comparing to the mean and the variation in the distribution. She would be closer with this 81, even though the mean is lower, which is interesting. You notice how the mean is lower? So be like, oh, she did better and the mean is lower, but there's more variation right here. So this is a tighter distribution because of the standard deviation. The standard deviation controls how wide the distribution is. And so, yeah, this is if we change it to this becomes a super interesting problem, which would be very hard to guess. But those are not the numbers. So we want to go back to that. And now we have the answer. 1.77, 1.29. Let's hope we solved everything correctly. Since she scored 1.77 above the mean, in economics, 1.29 above the mean in economics and 1.77 above the mean in math. She did better in the mathematics exam. Woo! Good stuff. Now, so just try to work this problem. Good morning, Meredith. Good to see you here. Thank you so much, everyone, for being here. Hashtag just be here and do some work. We're going to do a little 474, I think, but let's hop back to some Chapter 5, because Chapter 5 is a good one. What is this one right here? The minimum. Let's do this one really quick right here, and then we'll come back to Chapter 5. So let's do homework Q1. This was homework Q3. Let's knock out this one really quick, then we're going to do some BS 474. So what does this one say? Aptitude test. I don't know if I've done this one before. So we added some new questions this semester. 2703. Aptitude test. Uh-oh. What have we done? Aptitude test. Aptitude. Question right here. Hi, Professor. AirPods are dead on the quiet floor of Hodges, so it's going to be a lip reading day. Good to see you, Evan. Oh, no. People with z-scores of 2.25 above or above on a certain aptitude test are sometimes classified as geniuses. If Aptitude's test scores have a mean of this and a standard deviation of this, what is the minimum score needed to be considered a genius? Okay, so can anyone put the math in the chat? Can anyone put the math in the chat for this? Find the math for this. See if you can solve this without my help. I'm going to explain how to solve it. So the z-score tells us how many standard deviations something is above the mean. So anytime you hear a z-score, you should think, oh, I just need to go that many standard deviation. It was above because it was more than... Yes, because positive z-scores mean above, and this is going to be above also. So positive z-score, I think, is staying column. Does that make sense? If you're asking about this one right here. So we can kind of get an idea of what this looks like if we draw it out. And this is going to be one of the key to a lot of these problems. Makes sense? Nice. Who can solve this one right here while we work on it? And then we're going to hop over to 474, but drop those questions in the chat. That's not an amazing z-curve. We need amazing normal curves. That's better. Much better. We like normal curve like that. There we go. Good stuff. Been drawing normal curves for a decade. That's what you get. This is the optimum normal curve. Okay. So at the center of the curve, great job, Meredith. I think that's it. Yep. And Victoria's showing the math also. So you can kind of see the answer. If you put 100 here, you go to 108, 116, and then here would be 124. Now, we're not 3 standard deviations above the curve. I like to put the z-scores below the curve. We are somewhere right about here at 2.25 z-score. So this is a z-score of 2.25, and this can help you see that a z-score is how many standard deviations above the mean we are. At least in this instance above, it is away. If it is negative, so it would be below. So the observation is equal to the mean plus the standard deviation times the z-score. So we just need to plug in those values. We're solving for observation, so we need the mean, which is 100. We have the standard deviation right here, which is 8, and that's the standard deviation. That's the units. We go up and down, and then the last thing is the z-score, and the z-scores are all down here on the bottom. We're trying to solve for that, and the z-score is this. So plugging in, of course, Abby, what would you like to know, Abby? Drop it in the chat. Doing a little 474 next. There we go. 2 point. Nope. There it is. And just timesing this out right here, people are saying 118. Yep. 118, just solve it out right there. We'll do it really quick over here. Boop. Just put the calculator in. 8 times 2.25 plus 100. And if you notice, if you get these down, Victoria, are they seeming a lot simpler right now, like these ones right here, with the understanding of what a z-score is? If you know what a z-score is, you can solve them a lot quicker. Great job right there, Evan. Let's throw some points. But that's the goal, is if you understand what a z-score is, it becomes like, oh, well, it's just telling me how far it is above or below the mean in terms of standard deviation. So I'll just go that many up or that many down. That's awesome, Victoria. Just here in like 10 minutes or 15 minutes, I think you've progressed. That one is like the first few exactly. So we'll come back here, drop some more questions in the chat. We're gonna do a little 474, a little 320, drop some more 201 questions. Remember, we do have off-stars later today. Good work, Keith. Great to see you here. Head over to the main screen. So good to see everybody. Can we do question 4? Yeah, we'll put question 4 here next. We should be able to come back. BS 320 assignment 3, getting started. And let's see here, stat 201. Question 4, have you covered the Canvas content yet? Which one, Evan? Canvas content, stat 201, Canvas content number 3? Chapter 5. I think that's the one you're talking about. I think it is, maybe. Let me get, we're going to load up a little 474 right here as we speak. Surely it's not going to be good. It's having me like relog in like every day. My computer got fixed. I'm so excited about that. The one due tonight. I think we have done that one then. We can do that. That's the second one, right? We could do that, Evan. We'll try to get that in. We could do another version of it. So yes, I think we have done it, but we can just drop in and ask. Okay. This is my 29th time downloading it. Okay, let me get this going right here. Okay, I think we're good to go. With the timestamp. AirPods charged 34%, so chilling and watching now. Nice. Did they charge that fast? Like a supercharge? Ubot dropping some help in the chat right there. 3303. Let's do this. Okay, this is assignment 3, question 2C on BAS 474. So let's take a look at this. So my sixth question is first error part. Error if the condition. Oh, so your if, try getting it to work on a single case. So you're doing 2C right here, right? So using a for loop in either sequential or nested ifs, create a category variable called exclaim, where the value is in exclaim column is 0. So that should say none. Good to see you here, Jay. So what you want to do, and I guess we'll do a tiny bit on getting started right here. What you want to do, if you use ifs or if else's, you want it to get to work on one case. So remember that an if can only take, so you're getting the following error right here by using an if and doing something like this right here. That's where you'll get the error right there that it has condition as greater than length 1. So whatever you're evaluating right here, you might be evaluating a vector, but that's what errors occur. That's what error occurs when whatever is given inside of the if right here has more than length 1. So you've ran into that error right there where what you've put into there has more than length 1. But if we wanted to, so think about this. And then we should be able to, we can definitely do this with an if else or if. I think the easiest way to do this stuff is with an if else. So if you go here and go if else, like let's look at something right here. Let's go right here and load up a data set. And let's figure out, let's classify people as a tall male or tall female. If you look at the data right here, we have survey, gender, we have 386 females and 313 males. And then we also have the heights of the individuals. When is a male tall? When is a male tall? What height would a male be tall at? So when would a male be tall? When would a male be tall? Well, let's try to think. The answer. Oh, no worries. When would a male be tall? It's a totally subjective question. If someone says I'm tall, and then they're like 5'6", you're like, you're tall? I mean, maybe it might be for different distributions. I mean, maybe they're in 5th grade, and you're like, whoa, they're tall, 5'10", 5'6", and 6th grade, or that's wow. I don't know. Maybe they're 1st grade and they're 5'6". You're like, that's really tall. It's all context, right? We're kind of doing the same things we did before with Stat 201. 5'10" might be tall, and then maybe let's say 5 feet, but if you're 5'10", and you're female, you're probably very tall, right? I mean, that's pretty tall for a female. 5'10" is kind of tall for a male. We know that there's different like means for males and females. So we start to get a contextual idea for what's going on. This data set only has males and females right here, so that's why I'm talking in that context right here. So we only have to think about ways to categorize these groups within this data's context. And so with this right here, let's see if we have right here that somebody's survey $10 gender is equal to male and give me a longer condition I wanted. Their survey $10 $height. Wait, yes, is greater than, let's say 72, which would make them taller than 6 feet, then we will say tall male. I'm going to say other group. Look what I've done right here. Now, here's the key to this. Run it each time. I have not written all my code that I'm about to write here. I'm about to do a few more nestings on this. The key to this problem, write it in little bits. Run it each time. Do you see how I have this as working code? Does that make sense right here, Kevin? That this runs right now. Now, what I'm going to do is I'm going to go inside the other code right here. So inside the other code right here, I'm actually going to move it. I'm going to move this back up here to this line right so long because it's going to start to go to the other side of the screen. I'm going to go to this other group right here. I'm going to put inside of it an if-else again, and I could literally copy paste my if-else like this, and I've got my same code. I want to show you what I did is I took this whole thing right here that exists as this, and I'm putting it right here, and that's the idea of nesting. So now, let's say right here, if they are greater than or greater than, let's see right here, greater than, I don't know, let's go 52. And then let's say average male. And if you notice, this won't run. And why won't this run? I knew it wouldn't run, and I know why. Why does this not run? Try to debug my code here for a moment. This is where if you're running your code, all of a sudden you're, oh, I have an error. So now, what is my error? Your answer to this is very similar in theory. I'm working things in theory. You tell what to do if the condition. Good answer, Kevin. You are right. It does know what to do if the condition is true. That's what it does if it's true, and it's inside of the false right now. So it's inside of the first false, doing what it does if it's true right there. So you almost have it. You're very close. I think you see it, but it needs to know not what to do if it's true for the second thing it goes inside of. It needs to know what to do if it's what. Here, I want to show you because I think you're... Exactly, that's over here, yep. That's after this comma. So it reads through this comma and there's a blank argument. So let's put other group again right here. And you can see we have average male, tall male, other group. And so now we want to go right here and change the other group. Let's just say short male. So now we still have, but the short male is still a lot of people, or wait, short group, really? Okay, we need to finish this one up. I'm going to go inside of this because I'm inside of the false statement here, if else. I want it to sub indent like that. Good. If else. And then now we're going to go open this up right here, grab our thing right here, drop it in, and put female and... Because now we're going to have them, we want to say who the males are. We got to do one more thing with males. Less than, sure, we'll just classify the males because it's just continuously doing this. Probably would have been an easier way to do this, but it's just showing how to do the theory. Okay, less than, so let's put some boundaries. Greater than or equal to, greater than or equal to, less than 52, male, short male, and then last but not least, female. Do we still have the same amount of females? Okay, so let's store this as X. Let's run factor on X, and let's make a summary of here. Let's store it just to do it, and then let's make a summary of X, and we still have the same amount of females. We don't have any shorter males, though. Short male, if else, less than... Oh, are there no males who said they were that height? So maybe there were no males who said they were that height. I thought there was... Oh, 52 inches is super crazy. Like, not... That's very, very short. I meant to do 62. Like, very short. So I meant to do this. No wonder we don't have any individuals in that group. There we go. So how would I go about putting this? Well, this doesn't need a loop anymore. This doesn't need a loop. If you do it This did the whole goal. The whole point of, so if you want to do something in a loop, so to do something in a loop is if you have something like, let's say we're classifying people as short or tall. So you could say like over 6 feet is tall. We're just picking a height value. When we say like unusual or far away, like imagine if you saw someone who's 8 feet tall, that's like, whoa. We think of things as how unusual is something as distance from the mean, not like good or bad, not like it's good to be 8 feet tall or bad to be 8 feet tall. There's advantages and disadvantages to everything. I just want to make sure that's clear. So with this right here, will you finish up with this? The question I'm looking for you. Oh, which one is it, Evan, right there? Well, if you want to use nested if, so here's how to use a loop. So doing something similar with a for loop and if / else. So you can achieve the same goal we just did, which is going to be much longer, but you want to do it in parts right here. Like let's say we just want to classify someone as short or tall. So we'd go right here to our data. We'd go to height, and there's the heights. So let's say height greater than 72, greater than or equals 72, then we would have this as tall. Now here's the problem. If you go to if on this, the if right here is not going to work. So if we were to say if this is true, then tall, else right here, not tall. It's not going to work because we get that same error that you're getting, right? So this is the problem you're running into. Because how long is this vector? This vector is longer than length 1. An if, good to see your Meath. An if can only take a what, true or false? Quick question for the content quiz. Ignore them. Because we want to include them. No, don't just ignore them. Don't just ignore them, Meredith. Good question right there. We'll be doing that here soon. I think we'll probably swing back and do that. Like, yeah, I don't think the answer is ignore them, because we don't just ignore them. We give them special attention. Outliers get special attention. So something that sounds like special attention is probably right. I'll be doing it here in a little bit, but good question, Meredith. The others say exclude, but it might say like exclude and then talk about them, like do with and without. I might have to see it. But ignore them sounds like a very wrong answer. Like we never ignore them. We never toss them out. We never ignore them. We give them special attention. So something's going to sound like give them special attention, do the analysis with and without, maybe talk about, like, I'll check it out here in a moment, but good question, Meredith. So how long should that be in the if right there, Kevin? Like it should have length what? We see the error when we run this. And so it should, what does this mean? Because this is what we're jumping back to where you were starting at. What does this mean right here? Length has to be 1. That means it can only evaluate a singular true or false inside of here. Like it can't have the vector of all this. It needs a singular true or a singular false. Like whatever evaluates inside of this has to evaluate, if we were to run it, to a singular true or singular false. So a good way to tell if you have that is to highlight your code and run it. And this is not a singular true or false. It's a vector of trues and falses. But I can make it a singular true or singular false by going here to the first element and finding out that person is tall. Does that make sense what I did by going to the vector I'm using and only taking the first element of it? And then watch this. If I put an I inside of here, I could now go to the second element this easily. What have I made? What have I just made right here? What have I just made? You know him, you love him, he's back. What have I just made by doing that right there? Yeah, so, and that's it right there. And just throwing that I on there puts it from the whole vector to the singular case, and now I can go through and do this. And so that's got the skeletons in the chat. So does that make, like you said, that's huge right there. And once you see, you're like, oh, not a monster man. Just, well, it is a monster man. I like that. That's 100 points right there. He's a monster man. Sorry, Skeletor. Don't take it the wrong way. You're an unusual person, I think, or whatever you are. Yeah. So here's the thing, though, is don't write the whole thing out. Don't write the whole thing out. Get it to work on one case. Remember, do your codes in little bits right here. You don't see me coding the whole thing, even with what I coded up here, which looks pretty crazy, right? Like you look at this now and you're like, whoa, how'd you do all this? If you look at what I was doing, it might still exist on here. When I was running that, I ran it a whole bunch of times. Like if you look at how many times I run my code, I don't write a whole bunch of code and then run it. I write little code, I run it. I write little code, I run it. I write little code, I run it. keep running your code, because if you don't, you're going to have an error. It takes a second to run it, or it takes milliseconds to run it to check that it's doing what you want. And then once you run it, you're like, okay, it's still working. And you want to build it in theory as you do it. And that's how you get to be a better coder is, I try to remind myself, just run your code, just see if it's doing what you want. And then you check it out. Awesome. I think we're doing a little 320 here next. Okay, so I think we got that. So we built the skeleton, and then you want to build the code that goes inside of it. And we talked a little theory, a little 320 now. Okay, let's talk some 320. I figured out the rest of the homework, but couldn't do question 3 on the quiz. Ooh, let's check out some quiz. I actually submitted my sustainability SCMC homework to assignment 3 association part 1 homework. Oh, no worries. Just, yeah, we'll if I see that come up on any sort of checks or anything, I'll just remember that. My actual no worries, Peyton. Yeah, I would have probably saw it and been like, this doesn't look anything like the homework. So we're gonna talk some associations right here. And here, let's talk over the association assignment. People are great job knocking out the quiz right there, or the homework. Okay, let's get started on the BAS 320 assignment. Now, in the BAS 320 assignment, you need to first start by making an RMD file. Now, to make an RMD file, you go up here to plus and new ARM Markdown file. So an ARM Markdown file is something you can create into a Word document. That's what the Markdown file means, is you can turn it into something else, basically. So I'm going to go ahead and create this over here. And now it's good to go. I thought I was going to save my computer. What I often do is, and be very careful, I've got the RMD file code. I'm just confused on the follow-up questions. Yes, good stuff. So what I would do is make sure to delete all this. And once you knit your file, so I'm going to go here, start a file. I'm going to add in an R chunk so I know how to do that. Now, don't delete this R. Let's just call this first association. These have to have different names. Maybe I'm overthinking, but I thought I lined up with number. Explain in greater detail, Evan, right there. Lined up. Go in greater detail, Evan. Wait, 75%. Oh, okay, yeah. We'll do that here in a moment, Evan. You're talking about the Canvas content. Yep, we'll take a look at that. And so with looking at this right here, you want to make sure this works. Here, I'm going to see if it knits. Well, let me show you the buttons. You want to make sure this knit to Word. So you want to check this out. You want to knit early. It's saving to my computer. Brian's assignment 3. And it should be knitting. Takes that long to knit this little tiny file. So I don't knit to Word. A lot of times I knit to HTML just to check. So, and I'll show you that right here. A lot of times I'll knit to HTML to just check to see if it's knitting. You can knit to HTML. It just knits quicker a lot of times. So it just pops up an HTML window and you've got a web page right there. So does that make sense? Peyton right there, or wait, it's not Peyton. Abby right here. Do you have this right here? Can you knit your file? Are you good? You've got your wording, and then you can always edit what's in it after you knit. A lot of people don't realize that. It's like, wait a minute, I knit it. I can then edit what's in it. And you can always view what it looks like as a knitted file by looking at it right here. And you can also edit right here by going to this right here. So yes, my file's good. Nice job. So now Abby says, which is great questions, Abby, about the confused on the follow-up questions. Nice job, Peyton. Excellent work, Peyton. 100 points. So let's go look at those follow-up questions over here, and let me go grab them, because we're just doing associations. And now I'll be posting, I've talked to the grader. We're trying to get them caught up right here to make sure they're doing all the work. I want to make sure that the grading, it's a little bit behind right now. So we're talking to them about getting back and getting everything graded. Okay, let's go take a look at the assignment. Okay. So with this right here, interpretation of both marginal displays, make sure the practical or not practical significance is clear. Comparison of at least 2 conditional displays. Brief explanation of how the discrepancy value is calculated. Brief explanation of how the p-value is calculated. Interpreting the confidence interval for p-value, which is something we're going to be going over next class. And then right here, last but not least, your final test should come back. Statistically significant. Your first test, and your second test should not be statistically significant. Good stuff right there. It's going to probably be closer to 4 pages. It's just some people might be more verbose. And let me mention right here the biggest thing about the confidence interval, because I think that's the only part people might be stuck on, because I didn't go into detail on that yet. but let's look at that and literally explain how to do that part 5. So I'm gonna put a new section in the video right here, and definitely might even send an announcement and just say, this is the one thing we didn't go into great detail on. And let's put BS 320 right here, assignment 3, interpreting the confidence interval. Yeah, well, to make a contingency table, watch this. And I saw your thing, Meath, right there. So to make the contingency table, watch this. You ready? If we go here, and I'm going to use a data set I didn't have you use. You're using Survey 11, right? Let me double check. So I don't want to use the data you're using. Check out last class. Survey 11 right there, right? So let's go here and go data survey 10. Now you want to load reg class if you're doing stuff like this. Library reg class. Now we want to go here to associate, and we want to go here to handedness. Do not do these variables because these are survey 10. This is not your data. You can't do, does everyone understand? You can't do this one because this is survey 10 data. Someone put that in the chat for 100 points right there. No, you're good question right there, Meath. Hopefully I thought I answered it, but let me know. You can't do this problem because, yep, we are doing survey 11. You can't do this one because it's survey 10. This is the survey 10. This is not our data. Great job, Abby, right there. So I'm going to run this right here and let's take a look. Boom. Now, just tell me for a moment, what am I asking? Just put this good to see her summer. Similar but different work. You know how it goes right there. Meath, great job. What am I asking with this? Just explain to me. This code asks, is there a what with what? What does this code ask? And 201, some good stuff on the screen for you. What does this code ask? What does this code ask? Oh, so I'm going to make it a little bit better. Does gender... Great job right there, Peyton. Peyton, let's throw some 500 points. And that's, you could say, is there association? Does gender explain handedness? And so let's try to interpret this now. Is there an association between gender and handedness? Exactly, where gender is the X variable, and notice how gender's on the X axis, and handedness is the Y variable, and notice how handedness is on the Y axis. So looking through the outputs, you can see the answers to your questions, but let's talk specifically about the fifth one. If we were to get a p-value right here, the p-value is an estimated one via the permutation procedure, which means we can actually get a confidence interval for the p-value. Now notice, I am 95, or we say we are, this is just like stats 1 interpretation. We are 95% confident that the p-value is contained between the interval 0.678 to 0.759. So when it comes to this interval, interpreting the p-value interval, we come to two conclusions. The conclusions are, conclusive interval does not contain 0.05. Inconclusive interval does contain 0.05. And let me think, does, because it's weird to say it's conclusive and it does not contain it. I understand. So you want to come to a conclusion, right? So think about, when do we come to a conclusion on our p-value? So the p-value tells us what? What do p-values tell us? A p-value tells us if something is what? If something is what? Think SS. A p-value is used to tell if something is what? Statistically significant. Great job, Abby, right there. So we have right here p-value below 0.05, statistically significant. P-value at or above 0.05, not statistically significant. So if we draw this out, let's draw this out. What we get is we have a scale of numbers right here. And we'll pretend it goes from 0 to 0.20. P-values can only range between what and what. Now, I haven't done the full scale, but p-values can only range between what and what. Like if something is a p-value. So something is a p-value. Only 0 and 1, because p-values are probabilities. That's what the p of p-value stands for. So if we were to look at a p-value right here, and we got a p-value of, let's say, 0.03. Is 0.03 statistically significant? So is 0.03 statistically significant? Just simple right there. It is. It's below 0.05. But we can also make a confidence interval for it. And if we were to make a confidence interval for this p-value, we might get the confidence interval tells us the true p-value is somewhere between 0.01, sometimes it's not symmetric, to 0.06. So think about this. We think it is statistically significant, but it's possible that it's what? Like our best estimate shows that it is statistically significant, but it's possible it's what? Because we're trying to estimate what the true p-value is. So we estimate it to be 0.03, but the true p-value might be between 0.01 to 0.06. So it's possible that it might be what? It's possible it might be what? It might be above 0.05. It could be. It's possible it's not. So we would say that this is conclusive or inconclusive. Our test came back conclusive or inconclusive. Well, it's possible it might not be significant. So this goes to the p-value interval right here. So the p-value interval is what we want to look at right here for this interpretation, the p-value interval. And so we would say that this is what? It is inconclusive. So this one right here is going to be an inconclusive test. So that interval was inconclusive. But how about this one right here? Let's do a different p-value over here. This p-value was estimated to be 0.012. And then we got an interval estimating it to be somewhere between 0.10 and 0.014. Now this test, I'm back. No worries, Evan. This test, is it statistically significant or not? This p-value right here, is this statistically significant or not? Just the p-value. When we ran the test came back 0.12. Is that statistically significant or not statistically significant? That p-value that we found. We were like, oh, my p-value is 0.12. Is that statistically significant or not statistically significant? We're up here at the first part. We just look at the p-value. Not significant. Does that make sense? That's not significant. But I want you to look at the interval we created. This interval we created right here, what do you notice about it? What do you notice about that interval? That interval, think about the next part right here. That interval what? That interval what? It doesn't, so what does that mean? You're right, Meath. You're right, Meath. Great job. That's exactly it. Is conclusive. So think about this. You are basically certain that this is not statistically significant. Does that make to say you're certain or it's conclusive? You're like, oh yeah, it's not, like, it was not significant, and I'm really pretty certain it's not significant because when we estimate what the p-value is, it doesn't contain 0.05. So there's good evidence to believe that this is not statistically significant. It's conclusive. So think about this. We could do a different type of problem right here. Let's remove these. And we could do the same sort of work down here with a different fake p-value. Or let's talk about this. Whenever you get an inconclusive interval, what would you do? If your interval is inconclusive, let's look at the results right here. What would you do? If 0.05 is in the range, which means our interval is inconclusive, with this one is not, you would do what? You would run more whats. Think about the word down here. You would run more whats. And I'll show you how if you only run few of these, you get a very inconclusive interval. So now take a look at my interval right here. Do you see how my interval is super duper inconclusive? Abby, good question. We'll do on next. You got it. So what's the problem right here? My p-value is estimated to be 0. Ah, good question, Abby. So my p-value is estimated to be 0. So I should do what, though? Because this isn't a good way to run the test. I wouldn't run your tests this way. And I would also use a set seed. Seed equals. Oh, I didn't do a comma. There we go. Now my p-value is estimated to be 1. Increase the permutations. So you see how I have an inconclusive interval because I only ran one permutation. We could go up to 1,000 permutations, which is going to run more randomness procedures and give a better estimate. Do you see how this interval right here is smaller now? Watch this. If I go to 5,000, now look at the interval now. The interval when you run more permutations gets water. So there's from 70 to 75, and here's from 71 to 73. Running more permutations does what? No worries, Evan. Running more permutations will do what to the interval? Running more permutations will make the interval water. Because you're just running random. Well, it's not going to change the statistical significance of it. It's just going to give you a better estimate. More permutations will make the interval small. Exactly, it's going to make the interval smaller because you're running more estimates of it. It's going to make a smaller interval. Now, you don't know if the interval is going to go up or down. It's just going to be a better estimate. Does that make sense? So that's why it says if 0.05 is in the range, well, what will happen is when you run more permutations, your interval will get tighter. So this interval right here would go to something like, can we do this? It's going to shrink inward. I didn't grab the right stuff. But the interval would get tighter right here if you run more permutations. It could go up or down. And if it gets tighter, it's more likely to be what? If your interval gets tighter, the interval would be more likely to be what? Think about if something is tighter, then it's more likely to be what? Because we're going to keep making this interval smaller by increasing the amount of permutations. It's going to be more likely to be what? If you have a very wide interval, those aren't the actual values. Oh, Evan, great job, Evan. It's going to be more likely to be conclusive. Evan, 1,000 points. We like hearing that right here. And that's what we're trying to do is we're trying to show the theory behind how it works. And as Abby's seeing right there, it's going to be more likely to be conclusive because if you run very few permutations, you get a wide interval. And as you increase the permutations, your interval is going to get tighter. It might go up, it might go down. You don't know what's going to do. And now would this interval be conclusive or inconclusive? I'm just going to move around this interval right here. So this interval, we're going to take the x is where the p-value is at. Would this interval be conclusive or inconclusive right here? Think about your wording. Would this interval right here be right where I have it, conclusive or inconclusive? Conclusive or inconclusive right now? Careful. So inconclusive means it does contain 0.05. So this is conclusive. Does that make sense? It's conclusive. And is it statistically significant? The x, we'll do this. The x is where the p-value is at. And the interval is the interval right here. So the x is where the p-value is at. So no worries, no worries. You're fine, Evan. So this is a not significant inconclusive test. Think about this right here. We landed almost exactly where on this? This test now is what? Like if you look where the x is at, that was our p-value. So, or we could make it a little bit easier. See, there we go. Is that test statistically significant or not? Just look at p-value, where the p-value is at. That's just like a numeric value of 0.047 or something, because that's where the 0.05 line is at. That is it. Great job, Evan. That's statistically significant. P-value is below 0.05, but the test comes back what? The test here came back what? The test came back inconclusive. Inconclusive. Because you see how it does contain 0.05? So what's your suggestion to somebody right here? You're like, oh, your test is inconclusive. It might or might not be statistically significant. Like, we do think it is, but the truth might be that it is or is not, because the p-value is below 0.05. When you say contain, what does that mean? When you get the range of values right here, we're saying, here's what we think the p-value is. Run more permutations, exactly. So you might see this in your test right here. So think about what you have to interpret with this. When you're interpreting this interval, you probably want to say if your test was what or what. I would say, what about this p-value interval right here? I would say, looking at the p-value, I can conclude that my test is what? So this is how I would interpret this one. So this is like the answer portion. Looking at this interval, I can say that my test is what? Looking at that interval, I can say that my test is what? Make sure 201 is in 15 minutes. Looking at that interval, I can say that my test is what? And 0.05. I can say, yep, my test is conclusive. So I can be like, my test is conclusive because the interval does not contain 0.05, which means when I came to the conclusion that this is not statistically significant, I have confidence in saying that. Does that make sense? I think I'm going to see a lot. I got to be careful because if I say something like that, I think a lot of people might write that. Try to put it in your own words. That's going to help. Don't always write down verbatim what I say, but think about how this applies that correct. Well, that means we're basically sure of it, Abby. We're like, it's not statistically significant, and I'm sure of it. Does that make sense to say it's conclusive? So, like, this is where I want you to be like, oh, you're saying, like, it's not statistically significant, and I'm really sure of it because I've like concluded it. That's when we be like conclusive. We're like, yeah, it's not statistically significant. I'm very certain of that. It's like certainty to be like, yeah, the p-value is definitely above 0.05. That's what that interval tells me right there. Think about putting that in your own words to be like, yeah, that interval really indicates to me that it's not statistically significant because it's super duper above. It's nowhere even near 0.05. Like 0.05 is not even a belief I could hold. Does that make sense, Abby? To be like, that's giving you what you think the p-value might be because it's an interval to estimate what the true p-value is. And we think there's no way the interval is the 0.05 is the truth. It's like, nah, it's not statistically significant. We're really certain of this. And think about using words like that, like certainty. That interval is trying to estimate the true p-value. Yeah, we can be really confident. Look, it's a 95% confident interval. So I can be, it's at the very end of 201. Like we talk about confidence intervals. So I could say, I'm really confident that 0.05 is not the truth. So I'm very confident this is not statistically significant. I think Abby, someone was asking about number 2. We have just enough time to do that. We'll come back and do the other questions. The Canvas content, we'll do that a little bit later. Were you asking about number 2? That's really very distressing. Oh no. Question 2. Let me look at question 2. And we're going to do this for like 3 minutes because we got class in 10 minutes. 08 BAS 320 assignment 3 question 2. Comparison at least 2 conditional distributions. So when you look at a conditional distribution, we'd have to say given somebody is what here? Given somebody is what here? Where do we see the conditional distributions? Given somebody is what? And Meath was asking how to make a contingency table the longer way, and I'm going to show you how to do that while we say given somebody is what? Given somebody is male. Great job, Evan, right there. You see, look at that. Yeah, it's exactly what I wanted to hear. Given somebody is male. And there's a contingency table right there. I wouldn't do it this way because it's easier. If you look, we get the same values with the associate function or female. So given somebody is male, what is the probability they're right-handed? Now, you can do this the long way and go right here to 272 and divide it by the total, which you could talk about this, and there it is right there. But take a look. That's the conditional distribution. Take a look. Conditional distribution for y-handedness for each level of x. If there is no association, these should look similar to each other and similar to the marginal distribution of y. So take a look. Do male and female right-handedness look similar? And do they look similar? That's about 87%. That's 88. That's 89. Those look very similar to me. Male ambidextrous is 3.5. Female ambidextrous is 3.1, 3.2. And we can see it over here visually. Ambidextrous is virtually identical. They're very similar. So that means there's probably what between males and females in their handedness? There's probably an association or no association. So if there is no association, they should look very similar. So what do you think? We reverse it. Association means if we know someone's gender, it would tell us something about their handedness. There you go. It means there's no association. It means everything to do with handedness and gender is probably random chance variation. Because look at how similar these are. It's very, very similar when you talk about are males ambidextrous left or right, are females ambidextrous left or right. Well, the differences are just minor, and the discrepancy down here is very small, and the p-value is large. So we see a very small discrepancy, which is likely by random chance. A zero discrepancy would have the bars virtually, like literally identical. If the discrepancy is zero, there is no difference between the conditional distributions, and that's a conditional distribution right here. The marginal's over to the side. Some 201 stuff, right, Evan? So, and this applies to 201 also. So if you're hearing this and you're in 201, which Evan is, and Victoria is too, I think, we were talking about the conditional distribution of female, the marginal distribution of handedness, and then you can see right here that there is very little separation. If I were to look at a variable right here, we'll do one more one really quick from survey. I want to get one that actually shows an association. We'll end with that. I need to grab a different data set, and then we need to hop over to 201. I just love running data. Okay, so let's look at gender and need something that is actually... Let's look at gender and scholarship. I don't want to do it this way. Well, sure. Help me attach. No, we don't want to explain. We don't want the Y variable to know. We want gender to explain. You're welcome, Abby. Great work. Let's see if gender explains scholarship. My brother and sister both had scholarships. I didn't. Haha. Oh, no, I had an assistantship in grad school. That counts, right? Ooh, yeah. What do you see? Who is more likely to get a scholarship? Who is more likely to get a scholarship? If you look at this right here, now a lot of people have scholarships. Females are more like, and if you just look at this, given someone is female, the probability they have a scholarship is 76%, given someone that is male. So what is this right here? This is huge. Look at the differences, right? Just interpret really quickly. Females have about a what percent more likely than males to get scholarships. And I want to mention what you just found right here because it's a great place to end. When you say females have about a 10% difference, well, that's the answer. 10, great job right there, Evan. That's the practical significance. That's the number that matters. This is the statistical, and our test comes back conclusive that we think there is evidence of an association. So it is statistically significant. My test is conclusive, and the practical difference between the conditional distributions is about 10%. About 72% in general have a scholarship, but 66% of males versus 76% of females, rounding the numbers, which is the 10% difference, which is the practical significance. So the practical significance is comparing the conditional distributions. Does that make sense, Meeth and everyone? And you can get the contingency tables right there. But just interpreting this whole output, like the point of this assignment is to understand what this output is showing you, to understand how these expecteds are calculated, how the discrepancies are calculated. I didn't mention the discrepancy part, but to just talk about it. You're welcome, Peyton. With that, we're going to head off because I got class in 7 minutes. Bye for now, everyone. Bye.